Hello, my name is Mike McGlone. I'm a NASA Curriculum Specialist with NASA's Aerospace Education Services Project, and I'd like to share with you today some of the lessons and content from NASA's Summer of Innovation lesson plans. Today, in Part 1, I'd like to share with you an overview of the activities for the What's in Stars lesson plan. The history of stars is almost as old as the universe, going back to the Big Bang. Be sure to watch Part 2 of What's in Stars for more information. There are 3 activities in this lesson. The first activity is called Cycles in the Cards. This activity is related to NASA's research on stellar evolution based on data from the Chandra X-ray Observatory Telescope. Students will start with a set of stellar images, and based on information from the Chandra poster, arrange them in order of stellar evolution. Then they will compare the scientific cycle with the Native American legends of the Navajo people. In the activity Elements in You, students look at a number of different topics, starting with ideas about elements, the periodic table, and the formation of elements through fusion and stellar processes. In one activity, using simple pound cake, or pound cakium as the activity calls it, students will learn about elements and compounds. In another activity, students will build star models out of craft dough or clay and discuss the formation of elements in stars. An additional activity, again using pound cake, demonstrates fusion and its importance to the formation of those new elements in stars, which is explained in more depth in Part 2 of this video series. Another activity in the Elements in You lesson uses beads in a bottle to illustrate the distribution of elements in the universe. While another activity, which calls for a variety of food items, but I have modeled here with beads, looks at the elemental composition of a few common items in the universe. In the final activity, What's Out There, which is similar to a portion of the previous activity, students are challenged to look at mixtures of food items, or color beads as in the image, and determine the identity of the object, such as the sun or the human body. There are lots of fun activities in the What's in Stars lesson. I hope you will review the second video for more background information and enjoy sharing these activities with your students. Good luck. Hello, my name is Mike McGlone, and I am a Curriculum Specialist with NASA's Aerospace Education Services Project. Today, I'd like to share with you some background information and support in this Part 2 video to the lesson, What's in Stars. As Carl Sagan once said, to make an apple pie from scratch, you must first invent the universe, which means that all the natural elements we know come from universal processes, primarily in stars. The source for much of this lesson, and a great resource for teachers, is Your Cosmic Connection to the Elements, and the website listed below. The periodic table of the elements is an illustration of the fundamental building blocks of our universe, the elements, and how they interact. The most fundamental and most abundant element in our universe is hydrogen, and it was the first element to form after the Big Bang. The Big Bang theory is actually a collection of theories that have been used to predict phenomena and explain the formation of our universe. One of the major misconceptions that students have is that the Big Bang is a giant explosion, when in reality it is more like a massive, sudden expansion and cooling of everything in the cosmos. In the beginning, things were extremely hot. Matter and energy were expanding and cooling. At 1 second after the Big Bang, the temperature is 10 billion degrees, and we have a particle soup. It is really too hot and energetic for any nuclei heavier than hydrogen to form, so we mostly have lots of particles being created and destroyed. Protons, electrons, neutrons, positrons, and plenty of other ons. But things are cooling down pretty quickly. After 3 minutes have passed, the temperature has dropped to 1 billion degrees, and we see the first particles coming together. A proton and a neutron join to form deuterium, an isotope of hydrogen, as the universe continues to cool. From the deuterium, we can get helium. 2 deuterium nuclei join to form 1 helium atom. As the universe continues to cool, After approximately 400 million years, the first stars begin to form. And stars are important because most of the remaining elements are made in stars and stellar evolution processes. Only in astronomy can you call something the size of our Sun small, and so are stars smaller than about 5 times the mass of our Sun. These stars run on similar processes and share a similar fate. These small stars form the elements helium, carbon, nitrogen, and oxygen in their cores through the process of fusion. Elements in small stars are formed through fusion that occurs at the temperatures and pressures at the center of stars. In small stars, that temperature is about 15 million Kelvin. These small stars, like our Sun, fuse hydrogen into helium in their cores. The energy comes from the slight excess of mass of the 4 input hydrogen as compared to the resulting helium. The mass gets converted into energy as shown via Einstein's famous formula E = mc squared. In part 1 of this video, we demonstrated this hydrogen fusion using pound cake. This works fairly well, but since the activity uses pound cake for another demonstration in another context, misconceptions may arise. So I would recommend using another material, such as marshmallows or craft dough, to demonstrate fusion. As our Sun ages, it will transform from fusing primarily hydrogen in its core to fusing helium. As this changes, the pressure and gravity balance of the star changes and expands into a red giant. When this occurs, hydrogen fusion in outer layers and helium fusion in the core creates elements to the size of carbon. As mentioned before, our Sun is a relatively small star, with many larger stars having a much greater mass and the ability to fuse heavier elements. These massive stars can produce the elements heavier than carbon. This periodic table demonstrates some of the fusion reactions that can occur in large stars. Notice that we're always moving from lighter to heavier elements from left to right. We've seen 4 hydrogen fuse to form helium, and helium fuse to form carbon. Carbon can combine to form magnesium. Helium and carbon can fuse into oxygen. Oxygen fuses into sulfur. Helium and oxygen combine into neon. And helium and silicon fuse to nickel, which decays into iron, the heaviest element that can be created in a star's core. In our activity, we make star models with craft dough. The models illustrated and described in the lesson plan are for large stars. To help students with misconceptions, I would recommend some small star models with helium forming in the core surrounded by hydrogen. As a large star begins to form iron in its core, energy is no longer released in the reactions to form elements heavier than iron. These heavier elements require the input of energy for creation. Again, like in our Sun, when it grows into a red giant, we lose the balance between internal pressure and the force of gravity, and the star collapses, which can lead to a supernova, which we have an animation of in the Space Telescope Institute. Supernova are needed to have the energy requirements to fuse the heaviest elements, such as gold. Supernova do 2 primary things related to the elements. First, the collapsing star generates the energy needed to create the heaviest naturally occurring elements, such as gold, and the supernova also disperses these elements into the cosmos. They are also a source for cosmic rays. If you notice some of the elements such as lithium were skipped, good. Although rare elements such as lithium are formed by fusion in stars, they are very unstable. Cosmic rays are high-energy particles, often the nuclei of atoms, moving at velocities near the speed of light. These cosmic rays can interact with hydrogen and helium to fuse into lithium, beryllium, and other rare elements. So if you look at a periodic table and the source of all the naturally occurring elements, we can see that some elements form in only one way, while other elements can form in multiple environments. But how much of each element do we find? One of the activities from the What's in Stars lesson has students looking at a bottle filled with various colored beads. Each colored bead represents a different element, and the ratios are outlined in lesson guide. But as you look at the bottle, I hope you notice which color is most dominant. Can you guess which color represents hydrogen? You guessed correctly, white. To paraphrase Carl Sagan, all things begin with the universe and are composed of the elements. So as we look at the activity where students analyze the composition of various objects illustrated with beads or other items, can you determine which bottle illustrates the human body or Earth's atmosphere? I hope you guessed correctly, and your students can try these exercises in 2 of the activities from What's in Stars. And by the way, the mostly orange one is Earth's atmosphere. From yourself to everything around you, that is your cosmic connection to the universe. The original PowerPoint used as a basis for this video and other resources can be found at this website. Understanding the elements and how they form in stars is fundamental to understanding how the cosmos works. I hope you and your students enjoy the activities and lessons from What's in Stars.